Okay, friends. We have done mixtures of strong acids with strong bases. We've done mixtures of weak acids with strong bases. And yesterday we looked at mixtures of weak bases with strong acids just at the very end. We will not be looking at mixtures of weak acids and weak bases because it gets too complicated. But when I say that, what I mean is we're not going to take F minus, which is a weak base, and put it together with HCN, which is a weak base, or sorry, a weak acid, and have HF and CN minus. We're not going to be doing calculations with something like that, okay? This was kind of what we did back in Unit 4, acid-base part 1. Do you remember what we did with an equation like this? Pardon me? Yeah, you would name which one was the acid and base. So this is the base, this is the acid, this is the acid, this is the base. What else did we do with it? Sorry? Yeah, we would see which side is favored, exactly, right? And do you guys remember how to do that? Which side is favored? Yeah, so you would say which is the weaker, which is the stronger, and the one that is favored will be the weaker. Okay, so, but we will not be doing calculations with that. So you're not going to have, because these are not going to go to completion, there's no sort of calculations like a titration. It would make no sense to titrate because titration is all about getting to the equivalence point when they have completely reacted. Are you going to get complete reaction here? No. Okay, but we will look at mixtures of a weak acid plus its conjugate weak base. Okay, but the key here is that you're dealing with a conjugate acid-base pair. So one of them is going to be on one side of the equilibrium, one is going to be on the other side of the equilibrium. You could also have a weak base plus its conjugate weak acid. How many of you know what buffers are from, say, biology or just somewhere else in life? What do? They maintain pH. They resist changes in pH. When you add a small amount of strong acid or strong base, I mean, they also resist it if you add some weak acid or weak base, but basically it minimizes, a buffer solution minimizes the change in pH when acid or base is added. So what we have is we're going to have an equilibrium, and we have, this is actually not a buffer yet. Not a buffer yet. This is just, you've got 1 molar acetic acid. What's the pH of this solution? Acidic, basic, or neutral? Acidic, yeah? And it's not going to be very good at a absorbing changes in pH. And the reason for that is that when we do a Rice table for this, we've got 1 molar acetic acid, and then we've got our plus X minus X, and we end up with a tiny bit less than 1.0 molar of the acid at equilibrium. Yes? That's a fairly high concentration. If I were to add some hydroxide to this system, what would happen? Yeah. It's going to react with hydronium. That's going to bring the hydronium concentration down, which will cause the equilibrium to shift to the right. And what will that do to the hydronium concentration? It will bring it back up again. To where? To close to the original value. And that's what a buffer is supposed to do, right? It's supposed to bring hydrogen ion concentration, or pH, back to close to its original value. So it could work if you added some base. But what if we added some hydrochloric acid? What would happen? Yes? We would increase the concentration of hydronium, and it would shift to the left. But we have a little problem here, because this is a very low concentration. What's going to happen as you add more and more hydronium? What's going to happen to the acetate ion? It's going to decrease. And you started at a very low value to start with. What will it eventually hit? It's eventually going to hit 0. And not very eventually, it's very quickly going to hit 0 because you have such a very low concentration. You're going to run out of the acetate. So would acetic acid be good for buffering, keeping the pH the same if we added acid? No, because it can't really shift very much to the left. And that is why. Okay, so let's write this down. What will the effect, will the shifting of this equilibrium be effective at bringing H3O back down to close to its original concentration if we add NaOH? Oh. If we had NaOH, we said yes, correct? And when we added hydrochloric acid, no, because it will try to shift left, but it will quickly run out of acetate ion and will no longer be able to shift. Okay, so it's going to try to shift left, but you're going to quickly run out of acetate and it will not be able to shift left anymore, and therefore the H plus concentration will remain high. how could we fix this? Right now, we have a fairly high concentration here, which is going to allow us to shift to the right for a fairly long while, right? It's going to take us a while to run out of 1 molar. Okay, what could we do to make it be able to also shift left? What could we add? Yes? We could add more acetate. In what form could we add acetate? Sodium acetate, absolutely. Okay, so we are going to add some sodium acetate. When we do this, the acetate concentration goes up. However, in response to this stress, the equilibrium will shift to the left, causing H3O plus to go down and CH3COOH to go up. Okay, so we had added some of this, it shifted this way. And so now what we have is we have CH3COOH. It's now a little bit bigger than 1 molar because we shifted that way. Our CH3COO minus is now a little bit less than 1 molar because we added 1 mole to 1 liter, but it shifted left. And hydrogen is now very low because we shifted away from the hydrogen. But what that means is anytime we add some hydrogen or we add some hydroxide, that system will be able to shift one way or the other. Is good? Okay. So we got high concentrations here and here. Will this new equilibrium be effective at bringing H3O plus back to close to its original concentration if we add NaOH? If we add NaOH, what happens? The hydroxide reacts with the hydronium and it shifts to the right. Okay, what if we add some HCl? This is going to go up and then it's going to shift to the left. Are we able to shift both ways? Are we going to run out of acetic acid? No, because we got a fairly high concentration. Are we going to run out of acetate? No, because we have a fairly high concentration. So since this solution is now able to resist a change in pH when we add a small amount of strong acid or a small amount of strong base, it is now a buffer solution. Sometimes people think that we have mixed an acid and a base together. Don't they just neutralize each other? And the answer is no, because they are both weak. They set up an equilibrium rather than going to completion in the neutralization process. Neutralization really requires either a strong acid or a strong base to go to completion. Okay? All right, so we're going to I'm going to get you guys to describe what the stress is here. And then what the shift is, what the overall change in hydronium concentration will be, and what the overall change in pH will be when we add HCl and when we add NaOH. Give that a try. for our HCl, what concentration is changing? Hydronium. Very nice. And H3O plus increases. So that would cause a shift to the left. What happens to our overall, what happens to the change in hydronium? Does it increase or decrease? Increase. Is that increase small or big? Small. Whoops, not just small, small. What about our change in pH? Overall, it would be a decrease. And again, it would be small. What is our stress when we add NaOH? What are we changing the concentration of? Hydronium. And hydronium would decrease. So we would shift to the right. So overall, the H3O plus is going to decrease, but it's going to be small. And the pH will increase, but it's going to be small. Yes. Why is it small? Okay, let me just check and see if on the next page I've got the picture. Do I have a graph? Oh, we have a graph. Okay. So in more detail, we're going to look at why it is small. So what we have is we have here our high concentrations here and here, and the hydronium concentration is low. And now we're going to add a small amount of HCl, so we have H3O plus is increasing. That's going to be a stress, so it's going to spike up. So on our graph, this is our concentration of H3O plus. And right here, at this time, this is where, at time t, we added some HCl. So that was our stress. Now, as the equilibrium shifts to the left, what's going to happen to the hydronium concentration? It's going to come back down. Okay, so the equilibrium is going to bring this back down. Okay. And so this right here is just a very small increase. Instead of, if you didn't have that buffering capacity, it would just go up and it would stay here. Yeah? And you don't want it to stay there. Not if you're wanting it to be at a, not if you're buffering it. If you're buffering it, you want it to stay at the same pH. So that means only a small change in H3O, which means only a small change in pH. So let's graph pH versus time when we add a small amount of HCl to the buffer. What happens at time t? They can just go in there. Both of them is fine. That's good. That's great. Thank you. H3O plus went up. So what happens to pH? pH goes down. And then, as we shift to the left, I'm just going to call it HA because acetic acid is too long to write. Okay. Okay, so as this goes up, we shift to the left, and H3O plus goes up, pH goes down, and as we shift to the left, what's going to happen to the H3O plus? Yeah. And therefore, what happens to our pH? The pH increases. So it's going to go up, nice curve. Where should it end? Close to the original, but not quite. Is this making sense? Cool. Excellent. Okay, same buffer solution. Now we are going to add a small amount of base. The hydronium decreases. Do we add NaOH? Produces OH. Hydronium will immediately decrease, which will cause it to shift to the right, which will mean that the hydronium will go back up. So our graph is going to look like this. Again, we have our concentration of H plus, or hydronium. NaOH is added and it takes a big dip. That is our stress. And then we have the shift as it makes more hydronium, and because it has shifted, we have only a small decrease. In H3O plus. So there's actually not a lot to buffers for the regular curriculum. This is almost all you need to know. There's just very little bit more than that. You need to know that you have to have both the weak acid and its conjugate base in high concentrations. So you can't just add the acid, you can't just add the base, you have to put a mixture of both. And when I say fairly high concentrations, anything in the 0.1, 0.05 kind of neighborhood will be fine. Okay, don't worry about it. It'll be obvious. You'll have like choices of like 1 molar or 0.5 molar, anything. It'll be obvious. Could you please graph the pH versus time when we add NaOH to the buffer? What should happen right when the NaOH is added? The pH should go up. And then what should happen? It'll come down, but not all the way down. Look at us using stuff from Unit 1. Yeah, we did concentration diagrams in Unit 1. Oh no, unit 2. I'm so sorry. This was unit 2. Small increase. Okay, blah, 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 blah. This is just reiterating what we said. If we had only the weak acid, would the system be able to buffer effectively? If we add OH, the OH has decreased, and therefore it's going to shift to the, can it shift to make more H3O plus? Yes, because there's lots of acetic acid. If we add a small amount of HCl, H3O has increased. Can the system shift to use up that extra H3O plus? No, because we are going to run out of our acetate ion. I don't know why I've said this like 3 times now, but it's okay. So the key point is that you need relatively large concentrations of both the weak acid and its conjugate base, so you won't run out of one or the other. And you should know, as you already mentioned, that you cannot go to the back room and get a bottle of acetate ions. You would have to get it as probably sodium acetate or maybe potassium acetate. Always choose it to make sure it goes with what kind of an ion? Well, we've got an anion. We've got our anion. It needs to be paired with a cation, and it needs to be a soluble cation. So it needs a cation partner. And you want the cation partner to be soluble and non-reactive. Now, our soluble cations are the alkalis, and who else is always soluble? All your alkalis are soluble. There's another one that's always soluble. NH4. Would NH4 be a good choice here? NH4 hydrolyzes, and so NH4 would not be non-reactive. It's going to mess with your pH because it's going to produce hydrogen of its own, right? So NH4 plus is soluble, but it hydrolyzes. So not a good choice. Okay, so you want to choose something like sodium or potassium. So to make a buffer, you must have the weak acid plus the salt of the conjugate base. And that is how you get a buffer. And in fact, if you have a weak acid and you have the salt of its conjugate base, you are going to have an acidic buffer that buffers at pH below 7. So if you want to buffer at pH 4, you'll choose a weak acid and the salt of its conjugate base. If you want to buffer above pH 7, can you guess what you would want to use? A weak base and the salt of its conjugate acid. So we have mixed buffers are either mixtures of the weak acid and the salt of its conjugate base, or the weak base and the salt of the conjugate acid. And remember, this one is going to be an acidic buffer, and this one is going to be a basic buffer. Both substances need to be at a relatively large concentration. Generally, you can think of relatively large as being greater than 0.1 molar, greater than or equal to 0.1 molar. I'm not saying that you couldn't buffer at 0.05 molar. It just wouldn't, the buffer could be more easily overwhelmed. Do you know what I mean? You could run out of one of the reactants or one of the products more easily. Okay, it depends on how much you're adding to it, how much acid or base you're adding to it. So in general, if you want an acidic buffer, you will use a what? Weak acid. And the salt of its conjugate base. I feel like I'm flogging a dead horse here. Like, let's repeat ourselves 7,000 more times. Okay, so for example, our weak acid, HCN, our salt is CN minus, and the conjugate base was CN. Write the equation formed for the equilibrium formed by the above system. And here's a hint, you're not going to put HCN plus NaCN. That won't get you there. You will need to put HCN on one side. And you'll need to put your weak base on the other side. So what would we need to do here? What else would go on the left-hand side? Nope. Water. Okay. So we want to have water. And then on the other side, what will we end up with? We have CN minus, hydronium, yes. So whenever you are writing a buffer system, you should have the weak acid on one side, you should have the weak base on the other side, and you should have water in the reactants, okay? That's going to be the same if we could have our weak base in the reactants, and we could have our weak acid in the products, and we would put our water in the reactants, okay? So in general, if we want a basic buffer, one that buffers above pH 7, what will we use? A weak base and the salt of its conjugate acid. So a weak base. Who is our most famous of all weak bases that you guys still forget? Ammonia. NH3. Okay. So here's our weak base, NH3. Here is our salt. And here is our conjugate acid, NH4 plus. And we need to pair our conjugate acid in order to make it a salt. We need to pair it with an anion that does not hydrolyze and is soluble. Who is a good anion that does not hydrolyze and is soluble? Nitrate is good. Okay. Chloride and bromide, their conjugate acids are strong, so they are also good choices. There's no solubility issues with them unless you're working with silver or lead. But nitrate is always a good fallback because we know it doesn't react with anything. Okay? We know it doesn't precipitate with anything. But chloride and bromide are pretty darn soluble with most things. Okay? Here I've used NH4Cl. That's fine. All right, so we have, if we had NH3 at about 0.7 molar, what would we want the NH4 to be at, NH4Cl? We would want it to be at approximately what concentration? 0.7 molar. You want them to be approximately the same. And relatively large. Please write the equation for the equilibrium formed by this buffer system. And again, you do not want to write NH3 plus NH4Cl. That will not get you in the right place. So you want your weak base on one side, and you want your weak acid on the other side. Yes? Probably. Everything's aqueous except water, which is liquid. Yeah. And what else should go in the reactants? Water. Okay. Water in reactants. And what does that mean our other product is going to be? It's going to be hydroxide. Okie dokie. And yes, you probably should put states in for all of these. Everything is aqueous except water, which is a liquid. Now, for AP, we will go into the math a little bit more and see how we can actually make a basic buffer from a weak acid and the salt of its conjugate base and vice versa. But mostly, like for regular chem, an acidic buffer is a weak acid, the salt of its conjugate base, a basic buffer is a weak base, and the salt of its conjugate acid. Huh? Did I talk too fast? Well, if you'd rather, we could just call this WASCABA. WASCABA, weak acid and the salt of its conjugate base. And we could call it WUBSCA, weak base and the salt of its conjugate acid. So WASCABA or WUBSCA. All right, that's going to give you your acidic buffer and your basic buffer. Buffer capacity. At some point, if you keep dumping strong acid into a solution, you're going to overwhelm the buffer, right? Or if you keep dumping strong base, you're going to overwhelm the buffer. And this is what we call the buffer's capacity. The higher the concentrations of the weak acid and its conjugate base, or the weak base and their conjugate acid, the higher those concentrations, the bigger the capacity of the buffer. Okay, the capacity is the limit of the, oh, that's not supposed to happen. It's the limit of the buffer. And that limit is hit when you use up all of the weak acid or the weak base. And the buffer's capacity is determined by the number of moles of the weak acid and by the number of moles of the weak base. The bigger the moles, the higher the capacity. The lower the moles, the lower the capacity. Hopefully that makes sense. If you don't have as much stuff, it can't shift as long. Of the following solutions, which has the greatest buffering capacity? Tell your partner which one you like.
I think we stopped sharing. I see the amount of people that are wearing masks today.
I've had people out for days and days, and then the person who was sitting next to them out for days and days. We had like a whole little pod over here. We had Sally and Umber and Malvika. You guys were all sick, yeah, at some point? At some point, yeah. Right? Like everyone's kind of falling, everyone's dropping like flies. If you're really concerned, I will tell you that for the 2 years following, like when we were in school, like for 2 years, I wore a mask every day. And I never got sick, not even once. So if you're like, I cannot afford to get sick between now and Christmas, even if you're not sick, you might be like, you know what? I'm just going to wear a mask. Because there's all kinds of other people in this school, and I'm going to wash my hands because who knows who's been touching this dust. You know what I mean? Right? You might choose to do that. I don't know. Maybe I should choose to do that. I don't want to be sick over Christmas, but I probably won't. Yes? Yeah. I was like one of the last people wearing a mask, but I was never sick. Never. Of course, I'm never sick now too, but like I feel like that's going to end at some point, right? It's just like at some point I'm just going to go down and it'll be ugly, but there we are. Okay. Well, I also get vaccinated with everything, every opportunity, right? Like, so I've had my flu vaccine, I've had my COVID vaccine. I don't know. But so has most other people too, so I don't know. I think I've just been lucky. Okay, who has the greatest buffering capacity? Is it A, B, C, D, or E? B, because we have the most moles, yes? So let's say we have a buffer and it is prepared using 1 molar acetic acid, 1 molar acetic acid, and we also have 1 molar of the conjugate base. Now we have 1 liter of this solution. What's going to happen if we add 1.5 moles of HCl to this 1 liter of this solution? H3O plus is immediately going to go up to 1.5 molar. Then what? Is going to shift. How far is it going to shift? Very far. Are we going to be able to buffer all of that acid? No, because we have 1 mole, 1 molar, and remember we have 1 liter of this solution, so that's going to be 1 mole, right? 1 molar, 1 liter, that's 1 mole. And if we add 1.5 moles to this thing, is it going to be able to absorb all of that acid? No, you're going to end up with 0.5 moles of the hydronium left. Okay? There will be an excess hydronium of 0.5 moles in that liter. So we have overcome the limitations of our buffer, and it cannot hold the pH constant anymore. Buffers remain relatively constant as long as only small amounts of acid or base are used. Key point. Next key point. Buffer systems cannot be made from a strong acid and the salt of its conjugate base, nor from a strong base and the salt of its conjugate acid. Why is that? Chat with your partner about that.
Physics.
Okay, why not?
So that goes to completion.
Because it goes to completion. Can you have an equilibrium that's shifting if a reaction goes to completion? No. Okay? No. Buffers have to have an equilibrium. There is no equilibrium, so it cannot shift. If you had a strong acid, you would be able to absorb lots of hydroxide, but you would not be able to absorb any hydrogen. If you had a strong base, you'd be able to absorb lots of hydrogen, but not any hydroxide. Yeah?
No. I know.
Okay, so a strong acid can absorb hydroxide, but its conjugate base cannot absorb hydrogen, and a buffer needs to be able to do both. It's not that it needs an H and an OH, it's that you need an acid and a conjugate base that is able to act as a base. With a strong acid, you have an acid and that can act as an acid, but you have a conjugate base that cannot absorb hydrogens. It cannot, like chloride cannot take hydrogens. It will not hydrolyze.
Right.
Yeah?
Something that can take the H.
You need something that can take the H, you need something that can take the OH. Pardon me?
I can do that to the OH with the H plus, right?
Yeah. A buffer needs a conjugate acid-base pair that can absorb hydroxide and that can absorb hydrogen. In other words, that the system needs to be able to shift in both directions. In other words, it has to be an equilibrium. And if you got a strong acid, do you have an equilibrium? No. I feel like, again, I'm like belaboring the point. Basically, you cannot make a buffer out of a strong acid or a strong base. So for example, if we were to add OH minus, this would decrease and this would shift that way and that would be fine. Yes? But if we add H3O plus, this would increase and that cannot go that way. So we're out of luck. Yes? Okay. AP only. Yes, sorry. Possibly. You don't need to say all of these things. You just need to say one of them. Like you need to say it needs to be in equilibrium so it can shift to absorb hydrogen and produce hydrogen. Okay? That would be sufficient. Like I said, I have written way too many words here. Or you can say it needs to be in equilibrium so it can shift. You know, like AP Chem only. There is an alternate way to make a buffer. You need an acid and you need its conjugate base. Can you think of a way to take an acid, say hydrofluoric acid, and add something to it so you would get its conjugate base? No. You could add something to hydrofluoric acid and it would make its conjugate base. You could add OH minus. So you can actually have a weak acid and you add a strong base to it and you end up kind of where we were yesterday. Do you remember when we had a weak acid and a strong base? And we ended up with both the weak acid and the weak base? So that's another way of making a buffer. So we could add NaOH, to a final concentration of about what? If we have 1 molar hydrofluoric acid, how much NaOH should we add to make a buffer? About half. So in other words, how many molar? 0.5. Okay, because we want half of it to stay as HF and half of it to be converted into F minus. And look, here's our RICFA table. Right, we got our final. This one we are using molarity. Probably we should use moles, whatever. I'm assuming there's no change in volume. We're maybe adding solid sodium hydroxide. So there's no change in volume. Okay, so if we start with 1 molar and we have 0.5 molar of the NaOH, then our limiting reactant is NaOH, because we have less of it. I should have made these moles. Let's make these moles. We'll say we have 1 liter of the solution. Yeah, a one liter of the 1 molar, which gives us 1 mole. Yes? Okay. I like it better in moles. It's just better for a RICFA table. Okay? So here we are. We've reacted 0.5 moles. And so we end up with 0.5 of our acid, 0.5 of our base. So now we have HF and F at similar concentrations. Similar high concentrations. Yes? Yay. Is good? Okay. Cool, cool. Now we have a buffer. Yay. So here is just a similar, it's just the summary. So to a large concentration of a weak acid, you are going to add enough strong base to neutralize about half the acid. That's going to give you a mixture of the weak acid and the salt of its conjugate base. Alternately, you could have a large concentration of weak base. What would you add to it? You could add enough strong acid to neutralize how much? About half of the base. And the result would be that you have a weak base and the salt of its conjugate acid. Okay, example 10. What salt could we add to 1 molar NH3 to make a buffer? NH4NO3 sounds good to me. Because we have a weak base. Wubska. We have a weak base and we have the salt of its conjugate acid. What concentration would we want the salt to be approximately? About 1 molar. We're not adding a strong base to neutral, or a strong acid to neutralize half of it. We're actually just directly adding the salt this time. Okay?
So the 0.5 is only for.
The 0.5 is when you're reacting with a strong acid or a strong base. Okay? Write the equilibrium system for this buffer. Did you put the acid and the conjugate base on opposite sides of the equilibrium? Did you put water in the reactants? Yay! Did you end up with hydroxide as a product? Yay! Would this buffer be best at buffering above or below pH 7? Above pH 7. Because if you have WUBSCA, if you start with a weak base and the salt of a conjugate acid, it's going to generally buffer better at a pH above 7. Okay? Like I said, that's not a complete rule. If we're doing calculations, we can make exceptions to that. But just as a general rule, qualitatively speaking, this is generally what happens. Why is that, though? We'll talk about that later. Is that okay? Okay. And for regular Chem 12, you don't even need to know why. You don't need to know why. You just be like, okay, weak base, salt of conjugate acid, that's a basic buffer. Done. Buffers are very surface level in regular chem, okay? What other type of chemical, not a salt, could be added to the NH3 to make a buffer? Yes, you could add a strong acid. Example, HCl, beautiful. About how much? I should have put that in here. About how much would you add? Yeah. Okay, explain how the addition of this chemical can produce a buffer solution. Show the relevant reactions. Well, what we will end up with is we will have the H will be all used up, right? Okay. And we'll end up with NH3 and NH4Cl. And then these two will set up an equilibrium. And that can shift when H plus or OH minus is added. Is good? If we had 1 liter of the 1 molar NH3, how many moles should be added? 0.5 moles of the HCl. Okay, so I'm going to get you guys to do pages 85 and 86. Did you want reference pages in Hebden for the quiz? Do you care? Okay. La 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 la. 4.12 quiz. Hebden. 4.12 and 4.13. And is there anyone wanting to write the quiz tomorrow? Not a lot of you. Okay, that's all right. I got a couple people in my other block. It's fine. I have a review for the entire acid-base unit. Do you want it today or do you want it later? Later? Excellent. Just thought I'd offer.